Our first speaker is Fabrizio Scarpa. So probably he can start getting the stage. He's coming from Bristol University. We hope all is going well in technology and everything is combined. And his research interests are in the field of mechanical metamaterials. He's designing, modeling, testing different cellular structures, and mostly accounting for structural integrity. And not only that, but also working a lot with composites. So that said, it means not working with one single material, but exploring different combination of them to have and to exploit advanced functionalities of these materials. I would also remark that he's working a lot with biocomposites and bio-based matrices, which that it's adding an added challenge in this topic. And we are really eager to hear your talk, Fabrizio. The floor is yours.
Thank you very much for the nice presentation, and again, I would like really to thank really the organizers, really, and the academic, but also really the industrial organizers of this very nice conference. And I'm from the Bristol Composite Institute of the University of Bristol, and I will talk about Hygromorph and poligromorph materials, from bioprinting to 4D printing. I hope that later some of these terms will be a little bit clearer. So, let me see. I will first start to give a sort of small background about really the motivation of the research that I will describe in this talk. I will then talk about programmable composites hygromorphs, metamaterials using natural fibers. I will insist especially on 4D printing techniques with natural fiber called flux. I will show how it is possible to make shape morphing structures from hard polymers to soft polymers, like hydrogel systems. I will then talk about a new concept, the poligromorph material, so actuators and structures that are sensitive not only to water, relative humidity, but also to hydrocarbons. And then I will finish with some general discussion. Obviously, what you will see during this talk is not done only by myself, and I really want, first of all, to acknowledge all the funders, but especially all the fantastic collaborators that have made some of the realization in this presentation possible. Sustainability is big in the academic R&D agenda in UK, but not only in Great Britain, but also at the industrial level. And if you look at the share of renewable materials in every type of industry is on the increase, certainly by 2050. Just really taken as an example this picture that I took from the Bridgestone website, and you can see that by 2050 there are no renewable materials within the stock of the product of that company. We may argue whether 2050 is too late, but we are where we are. So in any case, if you look really at materials with sustainable characteristics, those are the highest rate of global research and development growth. In particular, natural fibers for several engineering applications as a market is expected to grow up to $77 billion by 2026, with a compound annual growth rate of 3.9%, which is quite sizable. So the question that we have started to ask in my group is, can we find ways to develop adaptive structural systems out of sustainable materials? If you look at the architectural industry, they have been already started to solve the question from a long time. I just give you a couple of examples related to the meteosensitive pavilion developed at the University of Stuttgart. These are meteosensitive surfaces made out of 2 layers of different types of oriented wood. So there is a change of the surface when there are changes of the relative humidity surrounding the building and also the temperature. And you can also find similar examples at the Architectural School of the University of Toronto. So architects have been already playing with this kind of concepts from a while. So our further question is, can we use other active bio-based composite materials with load-bearing characteristics, but also using novel manufacturing techniques like 4D printing? In terms of natural fiber materials, there is a fiber which is extremely interesting, and is flax. Flax has got really a stiffness similar to fiberglass, and the properties of flax from a mechanical perspective have been known since antiquity. But as a composite, actually, has got also a long history in terms of reinforcement. The Gordon aerolite was a phenolic flax prepreg with 70% of volume fraction of flax, developed back in 1939, and was developed at the time also to find a sort of suitable solution to the lack of supply chain of aluminium alloys just at the beginning of the Second World War. And the Gordon aerolite as a composite was used also to prototype some fuselages of the Spitfire. Very interesting composites. At the time, they already started to experience these thermoforming processes that were allowing to make composite up to 7 millimeters of thickness. And 7 millimeters of thickness have been only reached recently for carbon epoxy composite, for example, in the wing of the Airbus A350 or similar types of composite. Already at the time they were doing that kind of work. Composite that was also quite interestingly insensitive to relative humidity. At the moment, Gordon aerolite is still the stiffest composite with natural fibers on the market, well, for what is available on the market. And in terms of stiffness, in terms of really of tensile strength, only recently some epoxy flax and 50% volume fraction reinforcement prepregs have managed really to reach the tensile strength of the material. Quite interesting, flax has got an hygroscopic expansion of 21% and 95% of relative humidity, which is the largest between the sort of the technical natural fibers that you can find around. So it's an interesting type of reinforcement, and in terms of adaptive structures, nature really suggests a way how to use these types of natural fiber composite as actuators. And the inspiration comes directly from the architecture of the pine cone scale. If you look at pine cone scales are made out of a passive layer, is a stiff layer with a low axial swelling, coupled with several multi-layer of active components. These active layers are soft with high radial swelling. In composite parlance, this is an asymmetric unbalanced type of laminate. Is a 0-90 with 90 at different early stacking sequences. But these types of configuration, when there are changes of relative humidity, allows, for example, to change the curvature from the dry state to a wet state. And inspired by pine cone scales, we have developed several classes of thermoplastic composite with PLA, but also epoxy, a shape memory epoxy flux composite with this kind of unbalanced stacking sequences. Just to give an idea what happens when you use this type of architectures with these types of at least epoxy flux fiber composites, and when you have changes in humidity, you can see in these quietly accelerated videos, the actuators, they have this type of in-plane coupling between axial and transverse deformation. They provide this kind of out-of-plane change of curvature when there are changes of the relative humidity, or when you take the actuators and you chuck them in water. And the final curvature depends on the architecture in these types of composites. So you have a one-to-one correspondence between the architecture, the type of composition, and the relative humidity. And the interesting fact that they can be also made using 3D or 4D printing. By 4D printing, we mean 3D printed structures with materials that evolve over time. And these types of actuators are actually load-bearing. They have a bending stiffnesses up to 14 gigapascal, which starts really to be quite interesting, and similar to equivalent type of composite that you will do using fiberglasses. And just to show you, when we use 3D printing, 4D printing characteristics, the type of really complex structures, this is a calla lily that forms when the relative humidity is changed from 20% to 50%. Flux is not the only fiber, or natural fiber that can be used for these types of actuators. You can also use kenaf, jute, coir fibers. The matrix can be a thermoplastic, polypropylene, or maleic anhydride, not only the thermoset that we have seen before. Quite interesting, you can really make this type of hygromorph composites and then apply every type of sort of technique from kirigami, architecting, to obtain these types of metamaterials, which are bio-based in this case. And if you look at the actuation performance of these hygromorphs, this is quite interesting. If you plot the specific stress that provides the sort of the actuation authority, so maximum stress per density, versus the specific strain, so maximum strain per density that you can obtain, you will see that these types of composites, they sit nicely between shape memory alloys and hydraulics. From a certain point of view, they are surrogates or biomimicked units that are like really hydraulic pumps from a certain perspective. So in terms of really of actuation authority, these are quite interesting materials. We have made these types of composite using classical stacking sequence laminates and manufacturing processes, also using epoxy shape memory polymer matrices. The shape memory polymer matrices allows us to have 1 degree of freedom more in terms of design space. So we can combine initial moisture content inside the composites, the desired curvature also given by the stacking sequence, and the variation of the temperature through the TG of the polymer. And in other words, we did the same type of hygromorph actuator. We can store 2 different shapes, not the single one that we have seen before. And just to give you an idea, and what we can do in that sense, this is a classical example in soft robotics. You can see this handle with 4 fingers. The 4 fingers are the 4 actuators. And in that case, we start with a specific moisture content. We put really the ball in full immersion. And we then can grasp really the ball. So we are talking about a ball that is 20 times already the weight with a single actuator. So this exactly the same configuration, but now a 50% of relative humidity during desorption changes again already the shape, and we can still grasp the ball. So again, we have two ways really of grasping the ball in different environments. It's a different type really of passive configuration. Colleague, Professor Shinachi yesterday has shown some wonderful examples of really a completely passive type of actuation. This is another type, if you want, of passive actuation, but simply takes advantage of the surrounding environment. We have been also playing with these types of hygromorph to make metasurfaces, so complex surfaces with different types of curvature and shape. In this case, we also architect the metasurface using electroactive copper films for grasping. And so architecting the films plus positioning different types of hygromorphs with different types of characteristics, we start to obtain these sort of large handling capabilities. And just to give you an idea, this is a prototype that makes some autonomous actuation at 50% of desorption, and it has been architected in such a way that we have two series of hygromorphs that support these electroadhesive copper films. We have the change of the architected shape with the desorption. At the same time, we start to activate the electroadhesive copper films, and we can grasp directly this kind of very complex surface. Exactly the same type of metasurface can do also the double concave type of shape, because in that case, in desorption, because of the different type of architecture in a different set of patches, we can obtain now this type of double concave configuration, always with the same relative humidity in desorption. We start then to activate the electroadhesive copper films, talking about between 3.5 and 4 kilovolts per millimeter. And then we can grab a different, but yet complex surface. So what we have seen so far is very much really on the bio-based side, but it's also possible to use really softer materials. And we have been working on this class of bio-based alginate polyoxamer hydrogels with different types of composition, and we have developed really techniques really to control really the pore size at multi-scale level. And typically, the stiffness of these types of composite, static stiffness, quasi-static stiffness under compression, is between 90 and 130 kilopascal. The interesting fact is when you use this hydrogel base with particular classes of natural fibers and not necessarily flax, but another class that is under patent, and you use this composite to assess their vibration transmissibility properties, you obtain a sort of a damping material with a loss factor between 18 and 25%, but quite staggering, a dynamic moduli, which is between 7 and 15 times the static modulus within 100 Hz or 300 Hz. This is a frequency range that is actually quite difficult really to handle for most of the fossil damping materials are used on the market. And actually, the loss factor are increasing with the base acceleration. Quite interesting. We have done this test up to 3G. And in essence, it is a bio-based material with a performance equivalent to fossil elastomers. And we have a patent that is going internationally from April 2025. So, we have actually discovered almost by accident these properties, while we were really trying to develop the sort of the morphine capabilities of these types of hydrogels. So really lateral thinking and luck sometimes, they play a role in research. But this hydrogel base can also be used with the flax fiber that I've shown before. So we have done this composite alginate with flax fiber up to 5% weight fraction. These alginates are cross-linked with calcium chloride. They can be bioprinted, but they can be also made using dialysis techniques, so you can scale up the manufacturing. And the fibers are not long fibers that are embedded within the hydrogels. We ball mill, so the dimension of these short fibers are between 25 microns and 15 microns of width. But we have tested fusion resolution during printing, and what we have noticed that the flax fibers they enable really to make really close printing, like really sort of reinforced filaments that you will use in 3D printers with thermoplastic materials, and there is no particular fusing that we have observed, which is good for bioprinting and for the resolution really of high-quality structures. The flax also contributes to increase the viscosity, but this happens with flax fibers up to 1% of weight fraction. And the same types of stacking sequences that we have used with these types, with the previous types of load-bearing hygromorphs, have been used also to manufacture really samples here. What we have observed first is you have a general increase of stiffness with the increase of the weight fraction. This is expected, but because of really clustering reasons, the best tensile strength is always around, if you use only 1% of weight fraction. And also, if you look really beyond the 1% of weight fraction in terms of really stiffness, there isn't really a big increase. So diluted dispersions, actually, they already work quite effectively, not only in terms of reinforcement properties, but also to provide this type of shape morphing properties when we have changes of relative humidity in the surrounding environment. In this case, it's not only the flax that acts with the hygroscopic strain to provide the overall shape morphing. It is also the hydrogel that contributes really to the hygroscopic deformation. And you can see over there is an example. We printed really a rosette in wet state, and when it's put really in dry state for us is typically really 20–25% of relative humidity, we have this change of shape. If you're interested to more load-bearing characteristics for the printing, well, we have done already some work within this project in collaboration between the UK Defence Science Technology Laboratory and the equivalent in France, the AID, Agence pour l'Innovation de la Défense. And this is a partnership that we have with IRDL laboratory in Brittany. So we have developed really, the baseline materials, the baseline coatings and composition. And the IRDL, they develop really a special type of rig to make really long fiber PLA flax filaments. Something that needs to be really understood when you use natural fibers is the effect of the porosity of the fibers in the composites. composites made using natural fibers have not only porosity given in the matrix at the fiber matrix interface, but also inside the fiber itself, because of the presence of the lumen. So we have a multi-scale porosity, and you need to consider really the porosity in terms of efficiency of the actuation. And the porosity is also important to determine the characteristics of moisture desorption. So we had to develop a special type of measuring technique beyond the classical gravimetric technique in water that is used to assess the porosity of classical composites. So we made by thermoforming several PLA and flux composites. And in essence, if you really want to have really a good indication of the effective porosity in these types of natural fiber composite, you will need really to integrate a computational tomography scanning and water gravimetrics to identify bounds. And if you don't have access to the CT scanning, if you carry out gravimetric testing in ethanol is probably a better option, because we have seen that really they are slightly closer really to the CT scanning. Another aspect that in 4D printing is quite important is manufacturability. I'm quite happy that the previous talk was already raising some of those points, but especially when you use these types of long fiber reinforced filaments, you have all issues related to the initiation of fracture in the composite at the interfilament interface. These flux fibers are made out of yarns, twisted yarns, so you have problems with a yarn matrix interface. It depends also where you need to cut the sample, and then because you need to have those types of loops in order to make a really different stacking sequence actuation, really, you have this type of imperfection. And if you look in terms of general performance, in terms of stiffness, in plane shear and tensile strength and so forth, they're probably not the best in the market. But they provide also the actuation and still load-bearing capabilities. And just to give you an idea how their stiffness evolves with the moisture content or relative humidity, in the longitudinal direction, over there you see two different Young's moduli. In general, in this kind of natural fiber composite, you have almost a sort of a bilinear type of behavior under tension. So we take really two modules really to give this indication of stiffness. But you can see that there is a strong decay, for example, from 20 gigapascal up to really 7 gigapascal in the longitudinal direction. Transverse direction is obviously matrix dominated. In this case, it's PLA. So you go from 2 gigapascal to 0.7 gigapascal. It is also possible to use, with these 4D printing techniques, more sophisticated ways to design complex structures. And over there, we have developed this voxel-based finite element algorithm to deposit the filaments for target optimized curvatures architectures. Some of the speakers at the session before could suggest me really track loads of more sophisticated ways really to do better this kind of job. But what is also important again to consider is you need to incorporate really manufacturing constraints, because of the way that these filaments are deposited, really, you may have a really the model could provide really a good response on a single curvature, but on the transverse planes or local transverse planes, things may be a bit more fuzzy. And but in essence, these types of 4D printing techniques are quite flexible, and you can really design different types of morphing metasurface. I will conclude in terms of example to a recent piece of work that we are completing. It is about the development of poligromorph materials. What you have seen so far is responsive to relative humidity and water. But actually, in the sea, and not only in the sea, there are even more challenging environments in terms of composition. So we have developed this class of load-bearing composites using PVA and MAAPR. So we are talking about between soft and medium elastomers type of matrices and carbon fibers. And functionalized also in particular ways the matrices. And those composites can be used as actuators and sensors, both hydrocarbon and water environments. So they are sensitive to few vapors, water relative humidity, and quite interesting, the stiffness varies from the wet state from around 100 megapascal to upper intention up to 90 gigapascal. So we are talking about some considerable load-bearing characteristics. The architecture is very similar to the pinecone scales that we have seen before, but again, they react to different surrounding environments. I would say also more challenging because oil spillage is still really an ongoing problem. In conclusion, but I hope that I've shown really some of the capabilities of morphing adaptive structures to be made using bio-based materials. Hygromorphism is a very interesting concept because coupled with temperature, it becomes a sort of good general environmental trigger and provides also mechanism with high actuation authority. Considering not only water, but also other types really of surrounding liquid or vapor environments could be really an excellent way to expand the operational capabilities of these actuators. And they can be made either using classical composite techniques or 4D and also bioprinting, as we have seen. We think that we can also use it for different adaptive environments, and me too, I asked really the co-pilot to try to think about some application for submarines. But having said that, we had also really some initial thoughts about, for example, really hydrofoil, morphine hydrofoil being developed with this kind of techniques. And this is the end of my talk. Thank you very much for your kind attention.
Thanks for reading. Fabrizio was very, very self-explanatory, and it was very complete, I think, the overview. Thank you. Any questions? Maybe I can start. Very good. I like it.
Thank you for a very nice presentation, and it's nice to learn so much. So perhaps my question is a bit naive and stupid, but it seems to me that they are fairly slowly moving these morphing structures. So is there any hope, maybe is the right way to phrase it, to speed up the process of actually actuating them?
So the first answer to your comment is yes, they are slow. So we are with the best architectures and using epoxy and flux, 40% of volume fraction, we are talking about a time constant of several tens of seconds at best. Okay, so something that I haven't shown in this presentation, but is also possible to make fossil equivalent of these hygromorphs with carbon fiber. In that case, you need to use as a matrix something like polyamide PA6, which is a matrix that is humidity sensitive. So you turn from the from the fiber being the main agent and to the matrix being an agent. And in those cases, we have also deposited the equivalent of a PCB circuit. By Joule effect, we can increase the kinetics by 1 order of magnitude. Still, we are not talking about really, something fast, really for a Formula One race car. And besides, that would be also illegal. But speed of actuation is a limitation.
Any other question? Yeah, I think so, no? You wanted, well, do you want me to give it to you?
Yeah, thank you.
Here, thank you.
It was a bit of a follow-up with this question. You showed a very compelling case in the beginning, right, on using this for architecture and for the built environment, right? Because maybe you don't necessarily need to use it for applications where a fast actuation is necessary, but you can use it for something where your actual stimuli is slow, because then you don't care, right? Is there anything that you have probably considered or thought on applications of those kinds to responsive of ambient weather or things like that?
We have recently published a paper in which we show how to use these types of hygromorphs in applications like sun tracker. Mm-hmm. Interesting, the fossil version has been used for a prototype of a sun tracker in a ESA project, but for the moon.
Okay.
Okay, because over there is no... although they have asked also to consider some potential really vapor or relative humidity characteristics, because you never know what you can discover on Mars or one of the Jupiter moons. Okay. So sun tracker, adaptive release low antennas. This is something that... but I also have to say that flax is probably the best natural fiber, but there are also other natural fibers also that are already available really on the field that don't have the same hygroscopic strain, but still provide this kind of actuation authority. So there is a possibility also to try to make your own 3D printing on the field if you want.
Cool. Thank you.
Yeah. I have one question actually. Have you thought about local actuation? Because when you have that, this hygroscopic is along all the materials. So what if you just want to actuate one tip? I mean, I've seen that you have this double, but I'm talking more about on-demand actuation. So you put your system there, it's flat, and then I want it to respond now. Not just as I put it, but for example, 10 minutes later, and do it on demand. So whenever I want.
Okay. We started to answer partially the question when we developed these localized Joule effects on the fossil hygromorphs, so the carbon fiber polyamide type of composites. It also depends very much really on the structure and, as you say, also really on the scale. And the actuation. Certainly, with some of the hydrogel systems over there, you can have a relatively quick type really of dilatation effects when you check them really in solvent or really on water, and then I think it is also a question of the architecture, size, scale effects of the architecture of the component that you are considering, and the scale size effect of the material that you are considering within the component.
Yeah. I was also thinking about probably exploring hyperthermia or some materials that you can transfer local heat in your material.
Yeah, so there is a phase change.
Yes. So then you can really localize them in an area, and then it will be more than the rest of the material. Yeah. So you will have some bending. I don't know, to have degrees of freedom, right?
That's an excellent suggestion. Yes, absolutely.
Cool. Do we have any question in the room? So then let's thank you, Fabrizio, one more time.